So very happy to introduce our next speaker, Richard Guo, who will be talking on harnessing extra randomness, replicability, flexibility, and causality. And Richard is currently at Cambridge University, but is in the process of transitioning to University of Washington Biostatistics.
So I'll talk about this harnessing extra randomness, recent work joined with Rajan Shah at the Statistics Laboratory at University of Cambridge. So I will focus on what I call the randomized procedures. So these are the procedures where the output is a random function of the data. So to compute the output, you need the data, obviously, and also you need a way of generating extra randomness, typically by throwing a die or by pseudo-random generator. So the two pieces of information will pass through some procedure that give you an output and the score typically, and that could lead to a decision, for example, to acceptance or rejection of a hypothesis. Well, because of the extra randomness, so it's fairly possible that using the same data, but different piece of randomness, you could get a completely different result and hence a different decision. So it happens that I think nowadays, you probably would agree with me, such procedures are quite popular. One prominent example of such is data splitting, that is to randomly divide your data point into several paths for different purposes. So if I just do this division, this trivial division, it offers independence between the sample, which is quite valuable by itself, for example, to control overfitting and to prevent double dipping, which I will come back in a moment. There are other ways you can construct randomized procedures, for example, through sampling. You could introduce some rejection sampling, for example, into a procedure to retarget your data to some specific population for which you want to compute something of interest. As a plan for this talk, I will first try to convince you there are serious problems with the randomized procedure, and then I will present my method to resolve these problems, and finally show you some reasonably cool applications. So let me first start by trying to convince you there are problems with data splitting through two fictional characters I made up with. So imagine Bill, who's an economist, and Bill is interested in estimating the causal effect of a policy-making problem, which is whether or not offering cash bonus to those unemployed that could reduce their unemployment durations. Imagine Bill has collected some covariates that suffices to control the confounding between the cash bonus A and the unemployment duration Y. And he wants to estimate this causal effect and using now fairly standard double machine learning approach that Jamie just described. These would require, as we know, estimating two nuisance functions, the propensity score and the outcome regression. So the double machine learning approach would allow you to use ready flexible or black box methods to estimate these two nuisance parameters, and then typically using employing data splitting or cross-fitting to control the overfitting bias of those nuisance functions. This is how that works. You divide the data randomly into two parts, and on one part, I estimate the nuisance. On the other part, I use the estimated nuisance to evaluate my estimator. To cross-fit, I simply swap the rows of the two sample and do that again. I get another estimator. I take the arithmetic mean of the two estimators that defines a double machine learning estimator. Now, imagine Bill wants to use this method. He has the data loaded in his computer and he's ready to run, for example, the double ML package. And he just for safety, he sets the random C to his favorite number 42. Now that's the result he got. He got estimates is minus 0.1, was rather encouraging, and also the p-value is really significant. It's 0.004. But just imagine that he wonders what happens if we change the C to the next integer. All of a sudden, you seem to get a slightly different result, and particularly the p-value is no longer significant. The same can be said for the next random seed. So what would you do in such a scenario? So, well, Bill, as you may disagree, he thinks that he should just stick with the first result he got because 42 is the number he has been using since day one, and and by the way, this p-value, if I only stick to the first p-value, it is a marginally valid asymptotic p-value. So he feel quite justified in using the first result. He decided reporting the paper, and but just with a fine line that says, well, to replicate, you must use the same random seed 42 in this case. But as you can imagine, this could get criticized by the other readers, and we could question him, why I have to use your lucky number to replicate it. And you can also take it a little further to ask him, how do I know you did not fish for that special random seed 42? So this is obviously one problem, and let's move on to the next problem. So here's another fictional character, Laura, who studies cancer, in particular kidney tumor. And imagine she collected some kidney tumor sample, and these are cells in her test tube. And these belong to a patient diagnosed with specific subtype of kidney cancer, and there are many subtypes, and this belongs to a particular diagnosed subtype. And Laura basically wants to know if it is possible that there actually exists a new undiscovered type of kidney cancer cells within her sample. So she wants to answer that by this DNA sequencing data. This is some single-cell RNA sequencing data that takes the gene expression of many cells in her sample across many genes, typically hundreds of thousands of genes. So this question that Laura is interested in can be formulated as a statistical test. So basically, the null hypothesis is that all the cells are going to come from only one population distribution that is unimodal. That's on the left. And the alternative hypothesis that the cells could come from a mixture of different population distributions, then each of them have a different mode. So they come from from a population distribution of multimodality. So obviously you can see this is a well-posed statistical hypothesis test, and it cannot be readily addressed as what people usually do for the single-cell RNA sequencing data through some interactive analysis such as clustering algorithm. You can't really answer this question formally with a clustering algorithm. So what can you do? And here is a proposal. So imagine if all the cells that do come from one single unimodal distribution, then it holds that no matter in what direction I look at the data, the projection should always be a univariate unimodal distribution. In contrast, if the cells that come from a mixture of the different modes, then there must exist a certain direction. If I look at the direction, that should reveal a univariate distribution of two or more modes. So for testing unimodality versus bi or multimodality on the real line, this is a solved problem. For example, you can use this dip test developed in the 80s to solve this problem on the real line. Well, the remaining question is, how do we hunt for the direction to look at the data? Well, you could use any clustering algorithm to find the direction if you want. So this defines a procedure where the only caveat is that you can't really use the data twice. You can't use the data both to find the direction and to test the direct hypothesis along the direction. So what you have to do is to data split, to split the data to avoid the so-called double dipping. So this example is what I call a hunt and test procedure for hypothesis test. So imagine this is your data. Now I randomly divide it into two parts. Now on the blue part, I run my clustering algorithm that defines the two clusters. I connect the centers of the two clusters and define the direction, apply the direction to the other part of the data, and project the data along the direction and evaluate the dip statistic for those projections. And that is my p-value for testing this, for testing a hypothesis of unimodality on that line, and hence globally for testing multivariate unimodality. So suppose Laura coded up this procedure and wants to run it on her computer, on her data. She decided to run it for 10 times because, well, there's going to be this randomness. Now imagine these are the p-values that Laura got, and well, actually, only one of them is significant, and the other 9 p-values are not significant. So what would you say about these p-values? Well, I don't know. You probably would go with the same option as Laura. You probably wouldn't think there is enough evidence for you to say that there is a new subtype of cancer cells in the sample, because there is only one significance out of 10 times. But actually, you might be wrong, because well, actually, there could just well be a new subtype of cancer cells. What happens is that because the dimension is very, very high, the clustering algorithm will struggle to find the right direction. Actually, only 1 out of 10 times will find the right direction, and hence give the significant p-value. So this is another problem with the randomized procedures. So basically, the problem low power. So on the left, we have Bill. The problem is this extra randomness, is this high variability of randomized procedure. On the right, we have Laura, who suffers from this low power. So a natural solution to this is, well, I can apply the same randomized procedure multiple times for my data set and properly aggregate the information across multiple realizations. That hopefully would address the problem. So that's my proposal. And let me start with some settings. So imagine x1 through xn are ID sample from this underlying distribution P. I want to test the hypothesis. P is under the null H naught or the alternative H1. For that purpose, I construct what I call the single split statistic, which is a randomized procedure that accepts input x1 through xn and also this extra randomness omega. So I make one assumption, that is, the statistic is constructed such that under the null, you will converge asymptotically to a no asymptotic distribution, null distribution F naught. So for example, it could be a standard normal. If your statistic is a Z statistic, it could be uniform over a unit interval if your statistic is actually a p-value. So the randomized procedure single split test is just to compare one realization of this randomized procedure against the alpha quantile of this asymptotic null distribution and decide whether you want to reject the hypothesis. So now imagine we run the same procedure multiple times. I get Tn1 through Tnl by applying L independent rounds of your procedure on your data X. I call this vector of the statistics the exchangeable statistics. Why they are exchangeable? Because condition on the data, they're just IID because the randomness are IID. So marginally over the data, they're unconditionally exchangeable. So then I pull those realizations, I aggregate them with some predefined aggregation function S. I require this S to be a symmetric function, which is reasonable, and also a Lipschitz continuous function. Examples would include, for example, average, which is quite reasonable if you believe you have a Z statistic, sort of the signal is within the mean, so you want to take the average, or if you have a bunch of p-values, you want to aggregate through the minimum. Okay, so now what critical value we should use? So that's the only remaining question. We'll have to pick a critical value to run this aggregated test. And hopefully by choosing properly chosen critical value, we can reduce the randomness and also improve the power. Okay, so let's look at this aggregated statistic whose null behavior would depend on the joint distribution of those exchangeable statistics under the null. Well, this statistic vector's null distribution can be described into two parts, the marginal and the copula. The marginal, as we assume, you will converge under the null as some no distribution. But the copula is something, well, we just don't know. We know it's symmetric because it's changeable, but other than that, we don't really have anything to say about the copula. And therefore, because this unknown dependency or unknown copula, we can't easily come up with a critical value. Okay, so this is kind of a known issue in the literature, and there has already been some development roughly into two types that try to address this issue. The first type basically says, well, you make some parametric assumptions on the dependency and fit it to the data. But there are some quite simple examples, actually, you can construct where there is no good parametric model for the copula. You can show the copula is some really bizarre dependency model, dependency structure that not easily captured by any parametric copula model. So you can't really hope to use parametric models to guarantee the type 1 error control. Well, the other approach is rather pessimistic. Basically says, I don't know the copula, but just want to guard against the worst case. But As you can imagine, by doing that, you inevitably get very conservative tests. They typically can give you very, very low power. Okay, so I'm going to propose something different. So as we see, the challenge seems to be that we don't know the copula. We don't know the dependency of those exchangeable statistics under the null. So my proposal is, well, we can use some non-parametric method to estimate the copula and then put them together and therefore estimate the null distribution. So my proposal is actually use the subsampling, which is quite like Bootstrap, but requires weaker assumptions than Bootstrap to non-parametrically estimate the copula. So under the null, we have this null asymptotic margin distribution, and we combine this estimated copula by subsampling. We get these vector of exchangeable statistics, and then aggregate and query is alpha quantile, and that becomes the critical value for constructing the aggregated test. Okay, so here's roughly how that works. So we divide the data into big B subsamples, and every subsample you want to imagine its size is roughly n divided by log n. Now, suppose this is the first subsample, then I run L realizations of your randomized procedure. That gives me one row of this matrix, one realization of the randomized of this exchangeable statistic vector. I look at another subsample that gives me another realization. I do this for every of this big B subsamples. That gives me this subsample matrix, the B rows and L columns. Now I look at the entries of this matrix and replace every entry by its rank within the matrix. Okay, so now it's the rank. I normalize the rank by the total. I get this normalized rank. Now I claim at this stage, we have effectively estimated the copula using subsampling. Now I need to combine with the no margin distribution. So what I can do is to apply the inverse of this no marginal CDF function, no null CDF function to every entry of this matrix. And then we apply the aggregation function to every row. Now I have basically the rank transform subsample realizations of my aggregated test statistic. A query is alpha quantile that defines my aggregated test. That is a critical value. Okay, so what we can show about this method, under my assumption of this no asymptotic null distribution, we can show my method is asymptotic level alpha test. And under further assumptions on the behavior statistic over the null, our test is uniformly asymptotically level alpha. Okay. All right. About power. So under some assumptions about the local uniform convergence of the copula of those exchangeable statistic vector, we can show the power of the test is no different asymptotically than the power of an oracle test. That oracle test simply happens to know the true null distribution of the aggregated test statistic. Okay, so this is what we can show. And let me just get back to the fictional character story. So Laura's example is a hunt and test for what I call the conjunction hypothesis. Basically, a hypothesis written as a conjunction of simpler hypotheses. What it can do is your splitter data, use half of them to find the direction and use the other half to test a hypothesis along the direction. In Laura's case, these simpler hypotheses are unimodality posed on linear projections of the data. So this is to run what the earlier procedure, the single slit one, hunt and test procedure for multivariate unimodality under different settings. And we can use what I just described, the rank transform subsampling, to greatly improve its power. For example, this is by aggregating 50 realizations with aggregation function being the arithmetic mean. You can see immediately a power improvement. And this is using a different aggregation function, which is the minimum. And you see a different power improvement, particularly on a different on the bottom setting. And actually, we also provide adaptive procedure that tries to use the best aggregation function adaptive to the underlying data generating mechanism. So this solid red is kind of the automatic adaptive procedure that very competitive in terms of performance. And by the way, in these graphs, the tau equal to 0 is where you are under the null. So you can see the level is controlled. Okay. So there are other hunt and test procedures you can construct for other statistical testing problems. There are a few that I'm just listing here. Okay, let me get back to Bill about this problem with double machine learning. Actually, there are two problems with double machine learning. One, as I mentioned, is this extra randomness. The other actually is that the standard error of the standard double machine learning packages or approaches, they tend to be underestimating the standard error because it simply ignores the finite sample correlation between the different estimators belonging to different folds. So we can use our rank transform subsampling. Unfortunately, due to time limit, you may have to read the details in the paper. So basically, we provide a way to provide a better inference for double machine learning to construct better double machine learning confidence intervals, such that the randomness is greatly reduced, and also the coverage is improved, is much closer to the nominal coverage. This is a simulation example where the nominal is 95. And I'm looking at the double machine learning intervals coverage under different sample sizes and different number of splits. And you can see the double machine learning could be a bit under coverage. Through rank transforms correction, you can see a much better final sample coverage. Okay, I believe I have roughly 2 minutes left. Yeah, so if you don't mind, I just mention another example similarly different to causal inference. So you can also find, so as I mentioned, the sampling is sometimes useful for causal inference. This is a particular usage where you consider a two-stage sequentially randomized trial where A1 and A2 are two treatments and L and Y are two outcomes. The two outcomes are confounded by a latent variable. And you're interested in hypothesis in testing that the first treatment has no effect whatsoever at all on the final outcome for everybody in the population. But for a bit bizarre and interesting reasons that I think Thomas will mention in his talk, this constraint is not independence or conditional independence. It's not the usual things that we know how to test. It's something a little bit different. So this sharp null hypothesis actually can be formulated as independence or conditional independence, but in a different population. But in the population, this example, where the second treatment is not conditionally randomized, but rather completely randomized. But we don't have data from this population. Nevertheless, we can use reweighting, or in this case, resampling or rejection sampling to retarget the data to that population and use the off-the-shelf independence or conditional independence test for testing such a causal null hypothesis. And this also defines a randomized procedure. And as you can imagine, we can employ the rank transform subsampling to improve its power and reduce the variability. Okay, so let me summarize. So I think randomness can be quite useful for statisticians. Typically, is something that could allow you to repurpose some existing procedure or test to attack a new problem. But the downside, as I mentioned, is that it has higher variability and lower power. So our algorithm provides a kind of a meta algorithm that allows you to run many, many replicates and properly aggregate their information to reduce the variability and also greatly, hopefully, improve the power. So you're more than welcome to check out our paper and our R package multi-split from GitHub. Thank you very much.
Excellent. Thank you, Richard.